So the goal of this video is to prove the correctness of Casaraju's two-pass, depth-first search-based linear time algorithm that computes the strongly connected components of a directed graph. So I've given you the full specification of the algorithm. I've also given you a plausibility argument of why it might work, in that at least it does something sensible on an example. Namely, it first does a pass of depth-first search on the reverse graph. It computes this magical ordering. And what's so special about this ordering is then when we do a depth-first search using this ordering on the forward graph, it seems to do exactly what we want. Every invocation of depth-first search to some new node discovers exactly the nodes of a strong component and no extra stuff. Remember, that was our first observation about that was unclear whether depth-first search would be useful or not for computing strong components. If you call depth-first search from just the right place, you're going to get exactly the nodes of an SCC and nothing more. If you call it from the wrong place, you might get all of the nodes of the graph and get no information at all about the structure of the strong components. And at least in this example, this first pass with the finishing time seems to be leading us to invoking depth-first search from exactly the right places. So remember how this worked in the example. So in the top graph, I've shown you the graph with the arcs reversed. This is where we first invoke DFS loop with a loop over the nodes going from the highest node name 9 all the way down to the node name 1. And here we compute finishing times. That's the bookkeeping that we do in the first pass. So we just keep a running count of how many nodes we've finished processing. That is how many we've both explored that node as well as explored all of the outgoing arcs. And so that gives us these numbers in red, these finishing times between 1 and 9 for the various nodes. Those became the new node names in the second graph, and then we reversed the arcs again to get the original graph back. And then we saw that every time we invoked DFS in our second pass, we uncovered exactly the nodes of an SCC. So when we invoked it from the node 9, we discovered 9, 8, and 7. Those all have the leader vertex 9. Then when we next invoked DFS from 6, we discovered 6, 5, and 1, and nothing else. And then finally we invoked it from 4, and we discovered 2, 3, and 4, and nothing else. And those are exactly the three SCCs of this graph. So let's now understand why this works in any directed graph, not just in this one example. So let's begin with a simple observation about directed graphs, which is actually interesting in its own right. The claim is that every directed graph has two levels of granularity. If you squint, if you sort of zoom out, then what you see is a directed acyclic graph, of course, comprising its strongly connected components. And if you want, you can zoom in and focus on the fine-grained structure with one SCC. A little bit more precisely, the claim is that the strongly connected components of a directed graph induce in a natural way an acyclic metagraph. So what is this metagraph? What are the nodes and what are the arcs? What are the edges? Well, the metanodes are just the SCCs. So we think of every strongly connected component as being a single node in this metagraph. So call them, say, C1 up to CK. So what are the arcs in this metagraph? Well, they're basically just the ones corresponding to the arcs between SCCs in the original graph. That is, we include in the metagraph an arc between the strong components C and C hat, from C to C hat, if and only if there's an arc from a node in C to a node in C hat in the original graph G. So for example, if this is your C and this other triangle is your C hat, and you have one or maybe multiple edges going from C to C hat, then in the corresponding metagraph you're just going to have a node for C, a node for C hat, and a directed arc from C to C hat. So if we go back to some of the directed graphs that we've used as running examples, so if we go back to the one that at the beginning of the previous video, which looked maybe something like this, the corresponding directed acyclic graph has 4 nodes and 4 arcs. And for the running example we used to illustrate Casaraju's algorithm with the 3 triangles, the corresponding metagraph would just be a path with 3 nodes. So why is this metagraph guaranteed to be acyclic? Well, remember, metanodes correspond to strong components, and in a strong component you can get from anywhere to anywhere else. So if you had a cycle that involved 2 different metanodes, that is 2 different strong connected components, remember on a directed cycle you can also get from anywhere to anywhere else. So if you had 2 supposedly distinct SCCs, but you could get from the one to the other and vice versa, they would collapse into a single SCC. You can get from anywhere to anywhere in one, anywhere from anywhere in the other one, and you can also go between them at will. So you can get from anywhere in one. You can get from anywhere in this union to anywhere in the union. So not just in this context of computing strong components, but also just more generally, this is a useful fact to know about directed graphs. On the one hand, they can have very complex structure within a strong component. You have paths going from everywhere to everywhere else, and it may be sort of complicated looking. But at a higher level, if you abstract out at the level of SCCs, you're guaranteed to have this simple DAG, the simple directed acyclic graph structure. So to reinforce these concepts and also segue into thinking about Casaragiu's algorithm in particular, let me ask you a question about how reversing arcs affects the strong components of a directed graph. So the correct answer to this quiz is the fourth one. The strong components are exactly the same as they were before. In fact, the relation that we described is exactly the same as it was before, so therefore the equivalence classes of the strong components is exactly the same. So if two nodes are related in the original graph, that is, there's a path from U to V and a path from V to U, that's still true after you reverse all the arcs. You just use the reversal of the two paths that you had before. Similarly, if the two nodes weren't related before, for example, because you could not get from U to V, well then after you reverse everything, then you can't get from V to U. So again, you don't have this relation holding. So the SCCs are exactly the same in the forward or the backward graph. So in particular, in Casaragiu's algorithm, the strong component structure is exactly the same in the first pass of DFS and in the second pass of DFS. So now that we understand how every directed graph has a metagraph where the nodes correspond to its strongly connected components and you have an arc from one SCC to another, if there's any arc from any node in that SCC to the other SCC in the original graph, I'm in a position to state what's the key lemma that drives the correctness of Casaragiu's two-pass algorithm for computing the strongly connected components of a directed graph. So here's the lemma statement. It considers two strongly connected components that are adjacent in the sense that there's an arc from one node in one of them to one node in the other one. So let's say we have one SCC C1 with a node I and another SCC C2 with a node J, and that in G, in the graph, there's an arc directly from I to J. So in this sense, we say that these SCCs are adjacent, with the second one being in some sense after the first one. Now let's suppose we've already run the first pass of the DFS loop subroutine, and remember that works on the reversed graph. So we've invoked it on the reversed graph, we've computed these finishing times. As usual, we'll let F denote the finishing times computed in that depth first search subroutine on the reversed graph. The lemma then asserts the following. It says, first, amongst all the nodes in C1, look at the one with the largest finishing time. Similarly, amongst all nodes in C2, look at the one with the biggest finishing time. Amongst all of these, the claim is the biggest finishing time will be in C2, not in C1. So what I want to do next is I want to assume that this lemma is true temporarily, and I want to explore the consequences of that assumption. And in particular, what I want to show you is that if this lemma holds, then we can complete the proof of correctness of Casaragiu's two-pass SCC computation algorithm. Okay, so if the lemma is true, then I'll give you the argument about why we're done, about why we just peel off the strongly connected components one at a time with the second pass of depth first search. Now, of course, a proof with a hole in it isn't a proof, so at the end of the lecture, I'm going to fill in the hole. That is, I'm going to supply a proof of this key lemma. But for now, as a working hypothesis, let's assume that it's true. Let's begin with a corollary, that is, a statement which follows essentially immediately from the statement of the lemma. So for the corollary, let's forget about just trying to find the maximum finishing time in a single SCC. Let's think about the maximum finishing time in the entire graph. Now, why do we care about the maximum finishing time in the entire graph? Well, notice that's exactly where the second pass of depth first search is going to begin, right? So it processes nodes in order from largest finishing time to smallest finishing time. So equivalently, let's think about the node at which the second pass of depth first search is going to begin, i.e. the node with the maximum finishing time. Where could it be? Well, the corollary is that it has to be in what I'm going to call a sinc strongly connected component. That is a strongly connected component without any outgoing arcs. So for example, let's go back to the metagraph of SCCs for the very first directed graph we looked at. You recall that in the very first directed graph we looked at when we started talking about this algorithm, there were 4 SCCs. So there was a C1, a C2, a C3, and a C4. And of course, within each of these components, there could be multiple nodes, but they're all strongly connected to each other. Now, let's use F1, F2, F3, and F4 to denote the maximum finishing time in each of these SCCs. So we have F1, F2, F3, and F4. So now we have four different opportunities to apply this lemma, right? There's four different pairs of adjacent SCCs. And so what do we find? We find that, well, comparing F1 and F2, because C2 comes after C1, that is, there's an arc from C1 to C2, the max finishing time in C2 has to be bigger than that in C1. That is, F2 is bigger than F1. For the same reasoning, F3 has to be bigger than F1. Symmetrically, we can apply the lemma to the pairs C2, C4 and C3, C4, and we get that F4 has to dominate both of them. You'll notice we actually have no idea whether F2 or F3 is bigger, so that pair we can't resolve, but we do know these relationships. Okay, F1 is the smallest and F4 is the smallest. And you'll also notice that C4 is a sinc SCC in the sense that it has no outgoing arcs. And if you think about it, that's a totally general consequence of this lemma. So a simple proof by contradiction will go as follows. Consider the Strongly kinetic component with the maximum F value. Suppose it was not a sinc SCC, then it has an outgoing arc. Follow that outgoing arc to get to some other SCC. By the lemma, the SCC you've gotten to has an even bigger maximum finishing time. So that contradicts the fact that you started in the SCC with a maximum finishing time. Okay, so just like in this cartoon where the unique sinc SCC has to have the largest finishing time, that's totally general. As another sanity check, we might return to the 9-node graph where we actually ran Kazaraju's algorithm. And looking at the forward version of the graph, which is the one on the bottom, we see that the maximum finishing times in the three SCCs are 4, 6, and 9. Okay, it turns out they're the same as the leader nodes, which is not an accident if you think about it for a little while. And again, you'll observe the maximum finishing time in this graph, namely 9, is indeed in the leftmost SCC, which is the only SCC with no outgoing arcs. Okay, but it's totally general. Basically, you can keep following arcs and you keep seeing bigger and bigger finishing times. So the biggest one of all, it has to be somewhere where you get stuck, where you can't go forward, where there's no outgoing arcs, and that's what I'm calling a sinc SCC. Okay, so assuming the lemma is true, we now know this corollary is true. Now, using this corollary, let's finish the proof of correctness of Kazaraju's algorithm modulo a proof of the key lemma. So I'm not going to do this super rigorously, although everything I say is correct and can be made rigorous. And if you want a more rigorous version, I'll post some notes on the course website, which you can consult for more details. So what the previous corollary accomplished, it allows us to locate the node with maximum finishing time. We can locate it in somewhere in some sinc SCC. Well, let me remind you about the discussion we had at the very beginning of talking about computing strong components. We were trying to understand whether depth-first search would be a useful workhorse for finding the strong components. And the key observation was that it depends where you begin that depth-first search. So for example, in this graph with 4 SCCs shown in blue on the right, a really bad place to start a DFS call, depth-first search, would be somewhere in C1. Somewhere in this source SCC. So this is a bad DFS. Why is it bad? Well, remember what depth-first search does. It finds everything findable from its starting point. And from C1, you can get to the entire world. You can get to all the nodes in the entire graph. So you'll discover everything. And this is totally useless because we wanted to discover much more fine-grained structure. We wanted to discover C1, C2, C3, and C4 individually. So that would be a disaster if we invoked depth-first search somewhere from C1. Fortunately, that's not what's going to happen. We computed this magical ordering in the first pass to ensure that we look at the node with the maximum finishing time first, and by the corollary, the maximum finishing time is going to be somewhere in C4. That's going to be a good DFS, in the sense that when we start exploring from anywhere in C4, there's no outgoing arcs. So of course we're going to find everything in C4. Everything in C4 is strongly connected to each other, but we can't get out. We will not have the option of trespassing on other strong components, and we're not going to find them. So we're only going to find C4, nothing more. Now here's where I'm going to be a little informal, although again everything I'm going to say is going to be correct. So what happens now once we've discovered everything in C4? Well, all the nodes in C4 get marked as explored as we're doing depth-first search, and then they're basically dead to us, right? The rest of our depth-first search loop will never explore them again. They're already marked as explored. If we ever see them, we don't even go there. So the way to think about that is when we proceed with the rest of our for loop in DFS loop, it's as if we're starting afresh. We're doing depth-first search from scratch on a smaller graph, on the residual graph. The graph G with this newly discovered strong component C star deleted. So in this example on the right, all of the nodes in C4 are dead to us, and it's as if we run DFS anew just on the graph containing the strong components C1, C2, and C3. So in particular, where is the next invocation of depth first search going to come from? It's going to come from some sync SCC in the residual graph, right? It's going to start at the node that remains and that has the largest finishing time left. So there's some ambiguity in this picture. Again, recall we don't know whether F2 is bigger or F3 is bigger. It could be either one. So maybe F2 is the largest remaining finishing time, in which case the next DFS invocation is going to begin somewhere from C2. Again, the only things outgoing from C2 are these already explored nodes. They're effectively deleted. We're not going to go there again. So this is essentially a sync SCC. We newly discover the nodes in C2 and nothing else. Those are now effectively deleted. Now, the next invocation of DFS will come from somewhere in F3, somewhere in C3. That's the only remaining sync SCC in the residual graph. So the third call to DFS will discover this stuff. And now, of course, we're left only with C1. And so the final invocation of DFS will emerge from and discover the nodes in C1. And in this sense, because we've ordered the nodes by finishing times in a DFS with a reverse graph, that ordering has this incredible property that when we process the nodes in the second pass, we will just peel off the strongly connected components one at a time. If you think about it, it's in reverse topological order with respect to the directed acyclic graph of the strongly connected components. So we've constructed a proof of correctness of Kazaraju's algorithm for computing strongly connected components, but again, there's a hole in it. So we completed the argument assuming a statement that we haven't proved. So let's fill in that last gap in the proof, and we'll be done. And so what we need to do is prove the key lemma. Let me remind you what it says. It says if you have two adjacent SCCs, C1 and C2, there's an arc from a node in C1, call it I, to a node in C2, say J. Then the max finishing time in C2 is bigger than the max finishing time in C1. Whereas always, these finishing times are computed in that first pass of depth first search loop in the reversed graph. All right, now the finishing times are computed in the reversed graph, so let's actually reverse all the arcs and reason about what's happening there. We still have C1, it still contains the node I. We still have C2, it still contains the node J. But now, of course, the orientation of the arc has reversed. So the arc now points from J to I. Recall we had a quiz which asked you to understand the effect of reversing all arcs on the SCCs, and in particular, there is no effect. So the SCCs in the reverse graph are exactly the same as in the forward graph. So now we're going to have two cases in this proof, and the cases correspond to where we first encounter a node of C1 union C2. Now remember, when we do this DFS loop, this second pass, because we have this outer for loop that iterates over all of the nodes, we're guaranteed to explore every single node of the graph at some point. So in particular, we're going to explore at some point every single node in C1 union C2. What I want you to do is pause the algorithm when it for the first time, explores some node that's in either C1 or C2. There's going to be two cases, of course, because that node might be in C1, you might see that first, or it might be in C2, you might see something from C2 first. So our case 1 is going to be when the first node that we see from either one happens to lie in C1, and the second case is where the first node V that we see happens to lie in C2. So clearly exactly one of these will occur. So let's think about case 1, when we see a node of C1 before we see any nodes of C2. So in this case, where we encounter a node in C1 before we encounter any node in C2, the claim is that we're going to explore everything in C1 before we ever see anything in C2. Why is that true? The reason is there cannot be a path that starts somewhere in C1, like for example at the vertex V, and reaches C2. And this is where we're using the fact that the metagraph on strongly connected components is acyclic. Right, C1 is strongly connected, C2 is strongly connected, you can get from C2 to C1, and if you can also get from C1 back to C2, this all collapses into a single strongly connected component. But that would be a contradiction. We're assuming C1 and C2 are distinct strongly connected components, therefore you can't have paths in both directions. We already have a path from right to left via JI, so there's no path from left to right. That's why if you originate a depth first search from somewhere inside C1, like this vertex V, you finish exploring all of C1 before you ever are going to see C2. You're only going to see C2 at some later point in the outer for loop. So what's the consequence that you completely finish with C1 before you ever see C2? Well, it means every single finishing time in C1 is going to be smaller than every single finishing time in C2. So that's even stronger than what we're claiming. We're just claiming that the biggest thing in C2 is bigger than the biggest of C1. But actually, finishing times in C2 totally dominate those in C1, because you finish C1 before you ever see C2. So let's now have a look at case 1 actually in action. Let's return to the 9-node graph on which we actually ran Kazaraju's algorithm to completion. So if we go back to this graph which has the 3 connected components, and remember it's the bottom version is the forward version, the top version is the reversed version. So if you think about the middle SCC as being C1, playing the role of C1, and the leftmost SCC playing the role of C2, then what we have exactly is case 1 of the key lemma. So, which was the first of these 6 vertices visited during the DFS loop in the reversed graph? Well, that would just be the node with the highest name, so the node 9. So this was the first of these 6 vertices that depth first search ever looked at in the first pass. That lies in what we're calling C1, and indeed everything in C1 was discovered in that pass before anything in C2, and that's why all of the finishing times in C2, the 7, 8, and 9, are bigger than all of the finishing times in C1, the 1, 5, and 6. So we're good to go in case 2. We've proven, in case 1, we've proven the lemma when it's the case that amongst the vertices in C1 union C2, depth first search in the first pass sees something from C1 first. So now let's look at this other case, this gray case, which could also happen, totally possible, where the first thing we see when depth first searching in the first pass is something from C2. And here now is where we truly use the fact that we're using depth first search rather than some other graph search algorithm like breadth first search. There's a lot of places in this algorithm you could swap in breadth first search, but in this case too you'll see why it's important we're using depth first search to compute the finishing times. And what's the key point? The key point is that when we invoke depth first search beginning from this node V, which is now assuming the line C2, remember depth first search will not complete. We won't be done with V until we've found everything there is to find from it. Right? So we recursively explore all of the outgoing arcs, they recursively explore all of their outgoing arcs, and so on. It's only when all paths going out of V have been totally explored and exhausted that we finally backtrack all the way to V and we consider ourselves done with it. That is, depth first search in the reverse graph initiated at V won't finish until everything findable has been completely explored. Because there's an arc from C2 to C1, obviously everything in C2 is findable from V, that's strongly connected. We can get from C2 to C1 just using this arc from J to I. C1 being strongly connected, we can then find all of that. Maybe we can find other strongly connected components as well, but for sure, depth first search starting from V will find everything in C1 union C2, maybe some other things, and we won't finish with V until we finish with everything else. That's the depth first search property. For that reason, the finishing time of this vertex V will be the largest of anything reachable from it. So in particular, it'll be larger than everything in C2, but more to the point, it'll be larger than everything in C1, which is what we were trying to prove. Again, let's just see this quickly in action in the 9-node network on which we trace through Kazaraju's algorithm. So to show the role that case 2 is playing in this concrete example, let's think of the rightmost strongly connected component as being C1, and let's think of the middle strongly connected component as being C2. Remember last time we called the middle one C1 and the leftmost one C2. Now we're calling the rightmost one C1 and the middle one C2. So again, we have to ask the question, of the 6 nodes in C1 union C2, what is the first one encountered in the depth first search that we do in the first pass? And that again is the node 9. Okay, the node which is originally labeled 9. So that's the same node that was relevant in the previous case. But now with this relabeling of the components, 9 appears in the strongly connected component C2, not in the one labeled C1. So that's the reason now we're in case 2, not in case 1. And what you'll see is, what is the finishing time that this originally labeled 9 node gets? It gets the finishing time 6. And you'll notice 6 is bigger than any of the other finishing times of any of the other nodes in C1 or C2. All the other 5 nodes have the finishing times 1 through 5. And that's exactly because when we ran depth first search in the first pass and we started it at the node originally labeled 9, it discovered these other 5 nodes and finished exploring them first before finally backtracking all the way back to 9 and deeming 9 fully explored. It was only at that point that 9 got its finishing time after everything reachable from it had already gotten their lower finishing times. So that wraps it up. We had 2 cases depending on whether in these 2 adjacent SCCs the first vertex encountered was in the C1 or in C2. Either way, it doesn't matter. The largest finishing time has to be in C2. Sometimes it's bigger than everything. Sometimes it's just bigger than the biggest in C1, but it's all the same to us. And to recap how the rest of the proof goes, we had a corollary based on this lemma, which says maximum finishing times have to lie in sync strongly connected components, and that's exactly where we want our depth first search to initiate. If you're initiated in a strong component with no outgoing arcs, you do DFS, the stuff you find is just the stuff in that strongly connected component. You do not have any avenues by which to trespass on other strong components. So you find exactly one SCC. In effect, you can peel that off and recurse on the rest of the graph. And our slick way of implementing this recursion is to just do the single second DFS pass where you just treat the nodes in decreasing order of finishing times. That, in effect, unveils all of the SCCs in reverse topological ordering. So that's it, Casaragi's algorithm and the complete proof of correctness. A blazingly fast graph primitive that in any directed graph will tell you its strong components.